recording. So please start from zero. Yes. Please tell
Okay,
me
from the
again. Yes.
result,
Yeah. Yeah.
we
Yes.
stopped
Yes.
here, and this is the figure comparing different classifier with their accuracy. And as you show in the figure, the supporting vector machine and the RBF and the key nearest point, try one and two, achieved the highest accuracy, about 100%, while the other classifier shows significant low in the performance. And this variation indicates the sensitivity to the model selection and the high potential reliability concern despite the high peak of the accuracy. As the final result here is support vector machine, and the key one and two is the highest performer, and the higher the k, the value of the k will reduce the higher accuracy. Also, try to compare between the accuracy and the sensitivity and the error of the classifier. The figure illustrates the comparison between the performer of different classifier across three key metrics, which is the accuracy and sensitivity of the error of the error rate. For the supportive vector machine and the K1, K1 and K2, they stretch a high accuracy and the zero errors. Comparing with the linear, supportive linear and the binomial, they are very poor in the performer, indicate the high mode sensitivity, since they are sensitivity and detecting the imaging is very low. And also for the K classifier, the higher K value shows the reduced accuracy and decrease the error. Also, the final thing here we should take stronger classifier chief, and the higher the data set is gonna be resulting in the higher accuracy. For the reliability, we found that also the support vector machine has higher reliability, and the K3 and 5 uh, also resulting in the higher reliability, as I mentioned before. Reliability varies significantly across the classifier, as we see here in the fi- in the figure. The higher the number, the higher the reliability. Also, we should mention that the data set is very limited, so that's why we're getting different reliability here. Uh, Lastly, the discussion: the higher the accuracy does not guarantee the robust. Sometimes the accuracy is high, but is not guarantee that the performer of the model is going to be every time. So we need to increasing the data set and increasing the parameter, and also train different classifier to find the best fit classifier. Lastly, the conclusion and future direction. We should to address that here some limitation. Here we have small data set limited. So since we are dealing only with 120 imaging, so it's considered to be very low. And the reason behind that, we couldn't find any imaging that's higher than this number that's open for public. So some of them they require approval to get that. Also, the system dependent security also dependent only in the single point failure risk, and also the study only focus in ultrasound imaging, since they can diagnose the liver diseases with different machine such as MRI or CT scan. For the future direction, we should increasing the imaging, the number of the imaging. Also, they tried to to train different classifiers such as the CNN and robust to get a better extraction, and also we use different machine system such as CT scan or MRI, and also we improving using the AI system machine. Lastly, computer system can be improved, and if they improved, they will help many way, and will reduce the risk of liver disease. And this is a reference, the study. And any question?
Thank you so
Thank
much.
you.
Very good. Thank you, Mr. Abdullah.
You're welcome.
Yes. One person sent me a message, another Mr. Abdullah. Could you please share your screen?
Yes, doctor, yes.
Yeah, thank you. And your full name is
Okay, I sent the message, but I can present after Mr. Jafar.
oh,
So no
okay,
problem.
okay. Thank
Yeah.
you. Yeah, all right. So please share your screen. I don't know, Mr. Abdullah or Mr. Jafar. Who is the
Mr.
next?
Jafar, yes.
Yes, it's Mr. Jafar. Please share your screen.
Okay.
Uh, yeah, what is your Arabic name?
Jafar
Ja
Al-Aidarus.
so Jafar, I don't have a Jafar here. Why? You didn't upload yet, right?
No, no, no. After inshallah the
Oh,
session, I will.
okay,
Okay.
okay, okay, no problem. Yes, please.
طيب بسم الله الرحمن الرحيم. My name is Jafar Ahmed Al-Aidarus from biomedical engineering. And today I will present my project titled Reliability and Risk Analysis of Networked Patient Monitoring System in Critical Care Units. The case study focuses on patient monitor. The brand is Draeger company. Patient monitors connected to central stations across ICU, NICU, BICU, and CCU. This is abbreviation of critical care units in the hospital. Intensive care unit, neonatal care, intensive care unit, pediatric intensive care unit, cardiac care unit. The project is based on a real hospital monitoring environment and uses actual failure log data collected over a 24-month period in the hospital in Mecca. The main idea of the project is patient monitoring reliability should not be treated as the reliability of a single bedside device only. In critical care units, monitoring depends on a full pathway, sensors and accessories, bedside monitor, power support, network communication, central station, and so forth. The objective is to use real data and reliability engineering tools to identify the dominant failure source, estimate key reliability indicators, and propose practical improvement strategy for safer and more monitoring in critical care units. This slide shows the roadmap of the presentation. I will begin with a brief introduction to the patient monitor itself and why it's important in critical care unit. Then I will describe the case study scope, including the selected departments, number of monitors, central stations, study period, like this. After that, I will explain the problem statement and project aim. After that, literature review and research gap. The methodology section will be present analytical workflow, including reliability matrices, reliability block diagram, fault tree analysis, MATLAB-based calculations, and Monte Carlo as a supporting simulation tools. Okay. The system selected for this project is patient monitor. The brand is Draeger. Patient monitor is it's a multi-parameter bedside monitor used in critical care settings. to display patient physiological information such as ECG, respiration, saturation of oxygen, non-invasive blood pressure, invasive blood pressure, temperature, and related alarm information. In critical care units, this type of monitor is safety relevant because clinicians depend on it for continuous observation of patient status. If the device fails to acquire valid signal, if the displayed information becomes inaccurate, or if alarms are not generated and communicated, clinical response may be delayed. For this reason, the project doesn't treat the monitor as a simple standalone device. The monitor is part of connected monitoring pathway. In stationary use, it interfaces with docking and communication infrastructure, and that support power, charging, network connectivity, and central station visibility. Reliability in this project means more than whether the monitor turns on. It includes signal acquisition, valid parameter display, alarm generation, network communication, and the ability of central station to support staff awareness and response. This slide shows the functional pathway used the analysis. The monitoring process starts with patient physiological signal. These signals are captured by sensors, cables, ECG leads, for example, and other accessories. They are then processed and displayed by the bedside monitor. After local monitoring, the information passes through the network pathway to the central station, where staff can observe several beds from a centralized location. The alarm and response pathway is also essential because monitoring is valuable only if clinically relevant change are detected, displayed, and acted. Each block in this sorry. Each block in this pathway is a potential reliability dependency. A sensor or accessory failure may lead to inaccurate readings. A cable or lead problem may interrupt signal acquisition. A network or central station issue may reduce centralized visibility. An alarm configuration issue may affect alarm delivery or response. This functional view is important because it becomes the basis of the reliability block diagram and fault tree analysis later in this presentation. This slide summarizes the real case study scope. The selected fleet consists of 51 patient monitor distributed across four critical care units: ICU, NICU, PICU, and CCU. The ICU has 25 monitors and 3 central stations with 37 recorded failure. NICU has 11 monitors and 1 central station with 15 failures. BICU has 7 monitors and 1 central station with 10 failures. CCU has 8 monitors and 1 central station with 10 failures. In total, the analysis includes 51 monitors, 6 central stations, and 72 closed failure records. The study period is from January 2024 to December 2025, which is 24 months or 17,544 operating hours. The preventive maintenance cycle is annual by service provider. It's also important to note that no battery-related failures, because the lifespan of battery in this brand between 3 years or 4 years, like this. It's also important to note no battery, as I mentioned, related failures were recorded in the uploaded failure log. Okay. What about problem statement and project aim? The reliability problem in this project is that monitoring reliability depends on a chain of technical and operational elements, not on the bedside monitor alone. Failures may appear in several forms. The first is loss of monitoring, where the system can no longer provide continuous monitoring information. The second is inaccurate reading, where the system continues to operate but display unreliable values. The third, alarm failure, where alarm are not generated, transmitted, or displayed. Central station dependency makes the network and display pathway especially important. If bedside monitor is working locally, but the central station doesn't receive the information, and the staff awareness can still be affected. The project aim is therefore to evaluate real failure log data from network patient monitor, estimate reliability indicators such as failure frequency, MTTR, that's mean time to repair, and MTPF, mean time between failure, and availability. Use RBD, reliability block diagram, and FTA to identify failure pathway. And finally, develop a practical reliability improvement framework for critical care units. Literature review and the research gap. This slide summarizes the academic basis of the project. Reliability engineering. Reliability is commonly defined as the probability that a system performs its intended function under specified conditions for a defined period. This definition is directly relevant here because the intended function of a network monitoring is provide continuous valid of patient information. The literature and course material emphasize reliability indicators such as MTBF, failure rate, RBD, FTA, and data analysis. These methods support systemic assessment rather than relying on qualitative judgment. So from in patient monitoring system, network monitoring improve central visibility, but introduce new dependency, communication pathway, central station, alarm configuration, and workflow. And research gap is that these topics are often studied separately. This project integrates them into one system level case study using real failure log data from critical care units. What about the methodology overview? This slide presents the analytical workflow. The first step was failure log collection. The data set include 72 closed failure record from the selected monitors over the 24 months study period. The second step was data cleaning and classification. The third step was calculation of reliability matrices, include MTTR, MTBF, and availability. The fourth step was reliability modeling using RBD and FTA. The RBD translate the system into functional blocks. And the fifth step was MATLAB supported analysis, including scenario comparison and Monte Carlo simulation. Monte Carlo was used only a supporting tool in the test. So what about reliability matrices used? This slide defines the main quantitative matrices used in the analysis. MTTR means mean time to repair or restore service. It was calculated as total downtime divided by the number of the failures. In this project, MTTR reflects how long it takes on average or return the equipment or monitoring function to surface after failure event. MTBF means mean time between failures or failures. It was calculated as exposure hour divided by the number of failures, because this is a fleet level analysis. Exposure hours were calculated the number of monitors multiplied by 17,544 hours, which is the duration of 24 months study period. Availability was calculated using the downtime over exposure method, 1 minus total downtime divided by exposure hour. This method is suitable because we have recorded downtime values from the failure log. Okay, this slide summarizes the main indicator from the real failure log. The data set contains 72 closed failure record. The total record downtime was 915 hours over the 24-month period. The mean MTTR was 12 hours. The median downtime was only 0.78 hours. This difference is very important. It means that most events were short restoration cases, but a small number of long duration failures increased the average downtime. Average downtime. The estimated fleet MTBF was 12,427 hours, and the estimated fleet availability was approximately 0.99. This is a high availability value, but it should not hide the operational significance of repeated failures and long duration events in critical care environments. Another important result is that no battery related failures were recorded. Okay. In department level reliability results, this slide compares the department level results. The left figure shows normalized failure occurrence by department over 24-month period, and the right figure shows downtime per monitor. The ICU had the highest raw failure count with 37 records. This is expected because ICU also has the largest number of monitors and central station. The more important finding is that PICU and CCU show higher downtime per monitor. This means that they may have fewer records than ICU, but some of their events lasted much longer. This result demonstrates why a normalized analysis is necessary. Okay. This slide ranks failure categories by number of records. The two most frequent categories were network communication issue and central station issue. Together, these two categories accounted for 38 out of 72 records, which is 52% of all observed failure. This is a major finding because it directly supports the project focus on network-based monitoring system. If the project only looked at the bedside monitor hardware, it would miss more than half of observed reliability problem. The data show communication and central visibility and are major contributors to observed failure. Okay, this is one of the most important analytical slides in the presentation. It compares the failure categories by total downtime impact rather than by number of records. The key message is that frequency doesn't not equal impact. network and central station failure were frequent, but they generally had short downtime. In contrast, power-related failure, monitor hardware failure, and accessory failure were less frequent, but produced much larger downtime value. This has major implication for reliability improvement. If we only focus on the most frequent categories, we may reduce the number of interruptions, but still fail to reduce largest downtime contributors. Yes, this slide presents the top event analysis. The failure records were classified into three main top events: loss of monitoring, inaccurate readings, and alarm failure. Loss of monitoring was dominate top event by frequent and downtime. This means that many observed failure affected the system ability to provide continuous monitoring information or central station. Inaccurate reading had fewer records, but it had a large downtime impact. Alarm failure had fewer downtime hours compared with the other top events, but remains clinically important because even short alarm related problem may affect staff response and patient safety. This slide focuses on the central station pathway. In the data set, 41 out of 72 failure record affected to the central station pathway. This result is significant because it's confirmed that the central station is not minor add-on. It's a critical part of monitoring reliability, and critical care staff often rely on a central station to observe multiple patients and respond to alarm. The example image shows a bedside monitor status indicating a central monitoring issue. This type of event may not always mean that the bedside monitor itself is fully failed, but it can reduce central awareness. Okay, this slide shows downtime associated with severity groups. The key finding is that critical events were few, but dominated in downtime contribution. Only 12 records were classified as critical, but they contributed 687 hours of downtime. This means that a small number of severe events created most of the downtime. This support risk-based interpretation because reliability improvement should not simply count failures. It should combine failure frequency, severity, downtime, and top events relevance. This slide presents the functional reliability block diagram for network monitoring pathway. The block includes sensor and accessories, bedside monitor, power support, network communication, central station, and alarm response pathway. The purpose of reliability block diagram is not show every physical circuit inside the device, and instead it represent the functional dependencies required for successful monitoring. This slide shows simplified fault tree analysis. The FTA complements the numerical analysis by explaining how specific failure causes can lead to clinically meaningful top events. For example, loss of monitoring, the fault tree includes a network or communication issue, central station, unavailability, power failure, and monitor hardware. These causes can independently lead to monitoring interruption. So they are connected using OR logic. The second thing for inaccurate readings and for alarm failure. Monte Carlo scenario analysis is included here as a supporting tool, not as the main evidence source. The main evidence comes from the real failure log. Monte Carlo helps test how different improvement scenarios may affect expected downtime and availability under uncertainty. Okay, this slide summarizes the main interpretation of the result. First, the network pathway matters. More than half of the record failures were related to network communication or central station issue. This confirms that the analysis must focus on complete monitoring network, not only bedside monitor. Second, frequency and downtime are different. Third, loss of monitoring. It was the most frequent top event and remains the main focus on the FTA. Fourth, battery was not an observed driver. No battery-related failure were recorded in the failure log. Overall, this result shows the reliability improvement should system level, data and risk-based. This slide presents the proposed reliability improvement framework. The framework is based on the actual failure log findings, not only on the theoretical assumption. The framework has several connected pillars. The first one is connectivity reliability, because network and central station issue were the most frequent failure. The second is central station verification, because 41 records affected in the central station pathway. The third is accessory and cable management. Accessories may appear simple, but long duration accessory events can create major downtime. The fourth is MTTR reduction through spare parts, readiness, escalation, and workflow. The fourth, is MTTR, and the fifth pillar is alarm and the configuration control, because alarm reliability depends on not only on hardware but also on settings and by user. Okay. Okay, this slide presents the prioritized recommendation derived from the analysis. The first priority is connectivity verification during PPM, preventive maintenance after monitor relocation. This is justified because network and communication issue were most frequent category. The second priority is central station mapping and display check. This is important because 41 records affected the central station pathway. The third priority is accessory and cable is inspection replacement strategy. This recommendation is justified because accessory related events may create high downtime high downtime. The fourth is MTTR reduction through spare parts and escalation workflow. The fifth priority is mandatory asset ID and downtime recording. This will improve future device level reliability analysis and allow repeated failure tracking for individual monitor. Limitation and future work. This slide presents main limitation and future work. The first limitation is that asset ID were unavailable. I didn't include this ID because of this repeated failure analysis for individual monitors could not perform. The analysis was therefore conducted at fleet and department level. The second limitation is that the study relies on record failure events. minor unreported issue may not appear in the failure log. This is common limitation in field reliability analysis. The future work, the first recommendation is implement asset ID based failure tracking. Second, a monthly reliability dashboard should be created to monitor failure categories, downtime, and central station impact. Third, post improvement result should compared with current 24 months baseline. Finally, if available, future analysis could include user response and alarm response timing data. Main conclusion. The main conclusion of this project is that reliability of network patient monitoring is a system level property. It's shaped by bedside device, sensor and accessories, power support, network communication, central station, and maintenance practice, and documentation quality. The evidence from 72 real failure records over 24 months showed that network and central station issue were the most frequent failures. So power hardware accessory events downtime when they occurred. This is my references, and thank you.
Thank you so much. Very interesting. Yeah, very good. So, who is the next presentation? Please share your screen.
Okay,
Yes.
Abdurrahman here.
Yes, thank you.
Okay. Can you see the screen?
Yes, yes.
Okay. Assalamu alaikum warahmatullahi wabarakatuh. The project title is the Reliability and the Resilience Evaluation of Industrial Surveillance System using visible and infrared multi-sensor fusion and redundant communication links. The main idea of the project is to evaluate how the reliability method, engineering method can be applied to industrial surveillance system. Especially, I compare the traditional single sensor system with the enhanced multi-sensor fusion system. The focus is not only where the hardware works, but also where the full surveillance function is successful. I mean, detecting an event, transmitting the data, processing the information, and generating the alarm. The presentation is organized in 6 main parts. First, I will explain the problem and motivation. Second, I will describe the traditional and enhanced architecture. Third, I will summarize the methodology, including reliability block diagram, fault tree analysis, Monte Carlo simulation, and others. Then I will explain the implementation and assumption. After that, I will present the simulation result. Finally, I will conclude with the recommendation and main findings. Okay, in this slide, the industrial facilities such as refineries and power plant, chemical plant, and manufacturing sites required continuous surveillance for safety, security, and operation continuity. However, these environments are harsh. Cameras and communication system may affected. The cameras may affected by the fog, dust, smoke, and night operation, high temperature glare. Also, the communication system is affected by the electromagnetic interference. The main reliability issue in the traditional system or surveillance system, even on event, I mean on the single day CCTV camera, this can perform well degrading this camera can perform well during the clear daytime condition, but detecting capability can be decreased significantly at the night or when visibility is reduced. Also, the surveillance system does not depend only on the camera. Even if the camera detecting something, the data must be still transmitted through the communication network and processed by the control center and convert this to the alarm. So in the project, I will evaluate complete surveillance function. The detection, communication, and alarm generation. This slide shows the traditional baseline architecture. The traditional system is simple. It consists of equipment and the day CCTV camera, wired link, network devices such as switches and router. Then the video management system or VMS, and finally the alarm system. This architecture is useful as a baseline because it represents simple and common surveillance design. However, it has three main weaknesses. First, detection depends only on one type of the camera, which is day CCTV camera. Second, the communication depends only on one type of communication, wired communication. Third, this structure behaves like the series system. If any required block fails, the alarm may not generate it. This explains why the traditional system reliability drops sharply under the night or fog, dust, and smoke scenarios. The enhanced architecture improves the traditional system in two main ways. The first improvement is sensor diversity. Instead of using only day CCTV camera, the enhanced system uses four sensors: the day CCTV camera and the L-Ware camera and M-Ware and the S-Ware cameras. Second, the improvement is the communication redundancy. Instead of relying on one type of communication, the enhanced system uses both wire and wireless communication. After communication, the data processed through the network devices, then to the Fusion engine to combine all these images. After that, with the video management system and the AI modules and the alarm system. Okay. Here is in this slide, I will explain why multi-sensor improve their reliability. The day camera provide good visual details under clear condition, but it is weak at the night and in smoke or fog. L-Ware and M-Ware are infrared thermal sensors. They are useful at the night because they don't depend on the visible light. However, it is high temperature in high temperature environment. Their performance can be decreased because the thermal contrast become weaker. The S-Ware provide useful support in haze and low light and degraded, but it degraded visibility. In some degraded visibility conditions. The important point is that no single sensor performs best in every environmental scenario. Therefore, the Fusion improves system reliability by combining complementary strengths. If one sensor is degraded, other sensor may still detect the event. The methodology combines several reliability engineering methods. First, I used the reliability block diagram modeling to represent how the components are connected logically. Second, I use the fault tree analysis to identify how failures can lead to the top event, which is failure to detect and generate the alarm. Third, I used environmental degradation model to represent scenario detection probability under different conditions. Fourth, I used the MTBF, MTTR analysis and the resilience model to evaluate and perform the recovery after the disturbance. Okay. This slide here shows the fault tree from the top event, failure to detect and generate the alarm. The top event can be occurred during three major cases: sensor subsystem failure, communication subsystem failure, and or the control subsystem failure. For the sensor subsystem, the traditional system fails if the single day camera fails. In an enhanced system, there are 4 sensors: day, L-wear, M-wear, and S-wear. Because this sensor work in parallel, the enhanced sensor subsystem fails only if all 4 of the sensor fails to detect the event. For the communication, the enhanced system use wired and wireless link as a redundant path. Therefore, the communication is more reliable because one of the link can support the system if the other links fails. However, switches and router are still a required component. For the control subsystem, the Fusion Engine and the VMS and II module and alarm system must operate successfully. If one of these required components fails, the system may not generate the alarm. So the key point is that the surveillance reliability depends on the complete chain: detection, communication, processing, and alarm generation. The implementation was done using MATLAB, using Monte Carlo simulation. For each environmental scenario, I used 1,000 simulation trials. Each trials represent one detecting demand. The values used for MTBF, MTTR, detecting probability, environmental degradation factors, performance loss, and recovery rates are assumed representative values. They are not measured from the real installed system. In a real deployment, this assumed value should be replaced by the manufacturer datasheet, maintenance log, repair records, and field detection test result. The traditional system is successful only if the day CCTV detector detect the event, the wired or network path works, and the video management system operates. The enhanced system is successful if at least one of the sensors detect the event, the wired or wireless communication work, and the Fusion Engine, VMS, and AI module, and alarm system operate. This here is the 4 scenarios used in the simulation: the clear and fog dust. Third, the night scenario for the smoke and the high temperature. This slide showed the 2 types of input parameters. The first table showed the environmental degradation factor. This factor reduced the detection probability of each sensor and a different environmental scenario. For example, the day camera has a degradation factor of 1 in clear condition, but only 0.25 at night. This represents the strong effect of the low light condition on the visible camera. The Elware and Imware have high values at night because they are thermal sensor. However, they have lower value at under high temperature because the thermal contrast becomes weaker. The second table shows the MTBF and MTTR and availability values. These used for the in the simulation. This slide summarizes the Monte Carlo procedure. First, MATLAB calculates the effective detection probability for each scenario and each environmental. The MATLAB calculates the effective detection probability for each sensor and each environmental scenario. Second, the simulation randomly sample sensor detection and component operation states. For the traditional system, successful trials require three things: the day and detection. And communication through the wire and wireless, and successful famous alarm operation. The enhanced system successful trials required at least one of the four sensors to detect the event, successful communication through the either wired or wireless communication, and successful operation of the fusion engine, and the AI and alarm. The reliability estimate is calculated by dividing the number of the successful trials by the total number of trials. The failure probability is simple 1 minus the reliability. This represents the probability that the system fails to detect the event or generate the alarm. The reliability improvement is calculated by subtracting the traditional system reliability from the enhanced system reliability. This shows how much the improvement is achieved by using four sensor fusion and redundant communication. This slide presents the main reliability result. Under clear condition, the traditional system reliability is 0.89, while the enhanced system reliability is 0.99. Under fog or dust scenario, the traditional system drops to 0.49, but the enhanced system remains high at 0.98. The most important result is for the night scenario. The traditional system drops 2.22 because the day camera is strongly degraded at night. However, the enhanced system remains at 0.99 because the infrared sensor compensates for the weakness of the day camera. In smoke, the traditional reliability is 0.4, while the enhanced system achieves 0.79. The overall, the enhanced system maintains reliability above the 0.97 in all environmental scenarios. This slide here, I will explain why reliability results occur. At the day camera performance will very well under clear condition with the detection probability close to 0.9. However, however, it strongly degraded at night and in smoke. The Elware and Imware maintain strong performance at night because they rely on thermal radiation rather than the visible light. The Elware provide useful performance in haze and low light condition, and it is complement both visible and thermal sensor. Under high temperature, the performance of the LWare and MWare decreases because the thermal contrast between the target and the background is reduced. This figure supports the main reason for using Fusion. Each sensor has different strength and weakness, so combining these improve the robustness. For the failure probability and reliability improvement, in this slide here combines two important findings, failure probability and reliability improvement. The worst case for the traditional system
Sorry,
is
Mr. Jafar, to interrupt you. Could you please come to the next link? I'm sharing the next link. Thank you. Thank you.
okay.
Thank you.